Today we're going to be talking about TFX, which is an open source production ML pipelines platform that works mostly with TensorFlow. We're going to start with a little thought experiment. Try to imagine that you're an online retailer and you're selling shoes, and you have a model that's predicting click-through rates. And based on your click-through rates, you're deciding how much inventory to order. Suddenly, your AUC, your prediction accuracy, drops, not across your entire product line, but on one particular part, men's dress shoes. So why? You tested your model, you measured its performance, it was good, you put it into production. Why is it suddenly not doing so well? And more importantly, how do you even know that it's not doing well? Unfortunately, you probably find out, or you might find out anyway, when you order way too many shoes or not enough shoes. And that's not how you want to find out that your model has a problem in a production deployment. So the root of this is change. Change is a factor in all production ML deployments. It could be a big factor or maybe not so big a factor. Let's talk about that. For easy problems, things like recognizing images of cats and dogs, change is really not that much of a problem because the images in cats and dogs themselves don't really change that much. So you're going to be retraining your model based on improvements in your model or better data, and your data sets tend to be fairly easy to get. More difficult domains like styles and fashion and clothing, like our example here, those do change, and they change from year to year, from season to season, based on competitors and different geographies. Declining model performance is usually driven by change in your model performance. Retraining is usually driven by changes in your model performance. And labeling can be more difficult. Really challenging domains, such as trying to predict markets, where things change each day or maybe every minute, model retraining is very difficult. It's driven by model performance, but getting labels to drive that retraining is very difficult. And there's also things that can drive changes in your model, such as just changes in your business and changes in the data that you're receiving for your model. So let's think for a second about machine learning. When we initially think about a machine learning problem, we often focus on the model itself. And that's natural because we're probably trained as data scientists or machine learning engineers. And this is the part that research papers are written on, and it's the part that we tend to focus on. But in a production deployment, you discover that actually your model, we've measured it to be about 5% of your code. And all these other parts of your system are very important for maintaining and improving a production ML deployment. Unfortunately, people often find this out the hard way. So here's a famous tweet where someone took 3 weeks to develop a model, and it's 11 months later, and they still don't have it in production. So in production machine learning, we have all the normal challenges that we have for any kind of machine learning project or deployment that we're going to do. We need to, if we're doing supervised learning anyway, we need to find labeled data somehow. We need to worry about our feature space coverage and try to minimize our dimensionality. And we want to maximize our predictive information, of course. We also need to consider issues like fairness and rare conditions, especially in domains like healthcare or financial services. Rare conditions become especially important. And because our model lives for a long time, we need to think about the data life cycle and how we're going to manage that. But along with that, we have all the normal challenges that we have with any production software deployment. So things like scalability, modularity, testability, and safety and security. Google has done a lot of work and research in this area and published a lot of papers over the years. Here's a good selection. Certainly would be a great selection to get you started. I encourage you to look at these, and there's other papers out there as well. So what now? We have all these challenges. We have some research to look at. What do we do? Google's answer has been TFX, or TensorFlow Extended. And we created TFX because we needed it. And that was the first way that TFX was used. So it's used internally across Alphabet, including at Google, for most of the machine learning applications that we put into production. And it has been for several years now, and it's continually improved, of course. But it has a really good track record. And that includes at a lot of our partners, including Yahoo Japan. And also Twitter, which is an interesting case because Twitter actually came from a Torch-based environment. They'd made a big investment in Torch, and they went out a couple of years ago and evaluated their options going forward and ended up choosing TensorFlow largely because of the TensorFlow ecosystem and TFX. At a conceptual level, this is what a TFX pipeline looks like. And you'll see it mirrors the normal ML production process, or development process, rather. So at the beginning, we're ingesting data. Then we try to understand our data by generating statistics and a schema. We do some feature engineering. We train our model, and then we validate it. We look at its performance. And if it's good, we push it. At the top, you'll see those tasks that we're used to performing. In the middle are libraries that are open source libraries that are available today to use by themselves for particular parts of the process, but they're also leveraged by the components in orange as part of a TFX pipeline. So looking at it a little differently, this is a TFX pipeline. I refer to this as the hello world of TFX. This is where you start when you're first creating your first TFX pipeline. And on the left are the deployment targets. So from a training pipeline, you can deploy your model to a number of different deployment targets, including a serving cluster with TensorFlow Serving, or a mobile application with TensorFlow Lite, or a JavaScript environment, maybe in a web browser with TensorFlow JS. Or if you're just going to save your model and use it for transfer learning or generating embeddings, or maybe in an ensemble, you could deploy it to TensorFlow Hub. So those were the components, but what is a TFX component? There's three parts. There's a driver, executor, and publisher. The driver and publisher are largely boilerplate code that you probably won't change. The driver receives the input for the component, and the publisher receives the output from the component and puts that into metadata. And we'll talk about metadata in a second. The middle, the executor, is where the component does its work. And when you develop your own components, that's mostly where you're working, is in the executor. So a component pulls its input from metadata. It does what it's going to do, and then produces an output, which is then put back into metadata. And that happens over channels. There are input channels and output channels. And the input and output are metadata artifacts. And that's how components communicate with each other, how data flows through a pipeline. At the beginning of the pipeline, the first component will ingest data and produce its result and place it in metadata. And then components that depend on that artifact, that data, will pull it out of metadata and process it and then put their result into metadata, and so forth until you reach the end of the pipeline. So we've talked about metadata a little bit. Let's take a deeper look at it. So what is in the metadata store? There are artifacts, and artifacts have properties. So, for example, a trained model is an artifact, a data set is an artifact, a schema is an artifact, the results of an evaluation are an artifact, and so forth. Artifacts are grouped into execution runs. So each pass through the pipeline is an execution run. And if you want to try to understand all of the artifacts within that run, you can do that because they're grouped by execution run. So that allows you to understand the provenance of your data. A good example of that is trying to understand which data a particular model was trained on, or what result a metric was for, which model was that metric measured with. So along the way, we need to be able to process large amounts of data in situations that might require large compute resources. And to do that, we use distributed processing pipelines. And to use distributed processing, we use Apache Beam, which is an abstraction layer on top of other distributed frameworks, such as Apache Spark or Flink or Google Cloud Dataflow. There's also a very nice, it's called a runner, the direct runner, which you can run just on your laptop. And of course, it's not distributed, but it allows you to do development on your laptop without having to worry about spinning up or having access to a Spark or Flink or a Cloud Dataflow cluster. So Apache Beam supports a number of different frameworks, as we've just talked about, and a number of different languages through a number of different SDKs. And in the middle, you have Beam, which takes an operator or a data collection. It's called a P-transform or a P-collection from an SDK, and then translates that to the native API of whatever framework it's running on, which then generates a result. Or looking at it a little differently, you have a component which is running somewhere, either a full OS or in a Docker container. The executor of that component uses Beam. And to do that, it creates a Beam pipeline using the Beam SDK, which then is sent to a distributed processing cluster to do that processing. That result is then sent back to Beam and translated to a Beam result, which is returned to the executor of that component. So we've talked a little bit about components. There are standard components that come with TFX when you just do the first pip install, but you can also add your own custom components. We'll get to those later. Let's start with the standard components. Again, here is your pipeline. This is the beginning or hello world pipeline. It is a directed acyclic graph. So starting off, we have example gen. And example gen ingests data from a number of different data sources, and you can create your own custom example gen if there isn't an existing one for the data source that you want. So example gen will split your data into as many splits as you need, and it'll transform it or convert it into TF examples contained in TF record files. The next component is statistics gen, which calculates statistics across your data set. So in this part of the ML development process, we're trying to understand our data. We have some visualizations to help us do that. So for example, we can look at a histogram of a particular feature, look for missing values for that feature, and so forth. The next component is schema gen, which tries to infer the types of each of your features. Now, you may know more than schema gen does. Schema gen will make its best guess about what types those features are and what the valid values are for categorical variables. But if more than it does, you want to make sure that you look at that schema and make any corrections that you need to make. The next component is example validator, and it takes both of those previous results and looks for problems. So things like examples that have the wrong type of a feature, perhaps an integer where it was expected to have a float, or categorical values that occur so rarely that they might be actually incorrect. The next component is transform. And transform is where the feature engineering is done. So the code for transform could be a lot more complex than the components that we've just talked about because your feature engineering could be complex. One of the key things that transform does is to create a TensorFlow graph using the feature engineering that you want to do. That graph is then prepended to your trained model. So wherever you deploy that model, your feature engineering becomes part of what you deploy. You only have to write that code once, and there is no opportunity for training and serving skew. The next component is trainer, and trainer is doing it's training your model. Often this is TensorFlow training, but you could actually train other frameworks as well. The result is usually a saved model. Certainly for a TensorFlow model, it will be a saved model, which is then used by other components and your deployment targets. The code for trainer is about what you would expect. It's a TensorFlow model, first off, and then configuration parameters like the number of steps. You can also use TensorBoard with trainer to analyze the training process, including comparing execution runs or training runs on your model that may have been done months apart to try to understand how your model changed over time. We also have hyperparameter tuning, which works with trainer to tune your hyperparameters. And there's a couple of different algorithms that you can use. It's actually fairly easy to set up. The next component is evaluator. Evaluator does deep analysis of your model performance. And by deep analysis, it's not just looking at the top level numbers for your entire data set, but understanding particular slices of data that are relevant in your domain. So for example, you might be looking at different times of day and trying to make sure that your model performs well across different times of day, or different days of the week, or different languages, or geographies, or different types of customers. Infravalidator checks to make sure that your model can be deployed to your production infrastructure. It will try to load the model, and it optionally will run examples against your model and make sure that it can actually be used. If both evaluator and infravalidator agree that your model is good, and one of the things that evaluator does is compare it with the model that you already have in production, then pusher will push the model to production. You also have the option of using bulk infer, which if you're going to just do a batch of predictions against your model, bulk infer is a good option for doing that. So in addition to components in a TFX pipeline, there are also pipeline nodes. So what are pipeline nodes? Pipeline nodes are special purpose classes specifically for performing advanced metadata operations. So that includes things like importing external artifacts into metadata or performing queries of the artifacts that are in metadata. So there are currently two basic types of pipeline nodes. The first is importer node, and that's the node that is used to import an external artifact into your metadata store so that you can use it in your pipeline. The other pipeline node is resolver node, and that's used to perform queries of the metadata that is in your pipeline. So in the example here, we're looking at the latest artifacts that were generated by the example gen component, and we're looking for the latest 5. So we want a collection of 5, if there are 5 available, artifacts. There are 2 types of resolver nodes currently. The one we just looked at, the latest artifact resolver, and the latest blessed model artifact resolver, which is used, for example, by Evaluator to look at the model that you currently have in production. So it's going to pull the latest blessed model and compare that to the model that you've just finished training. You can also deploy models to TF Lite for mobile or IoT deployment scenarios. So to support that, we've added some additional support for it in TFX, and that includes rewriting your model to optimize it for things like mobile scenarios where you have limited compute and memory resources. So to do that, you're going to invoke the TF Lite rewriter as part of your trainer. And then you're going to use the rewriter factory to create and invoke that rewriter on your saved model. So as you can see, it's not really very much code. Then you also want to make sure you evaluate your model when it's trained for TF Lite. That's going to be slightly different, and you want to make sure you set that up correctly in Evaluator. So in addition to the standard components that we talked about, there are custom components that you can create. And there are 3 ways to do that. The first and easiest way is just to write a Python function and add a decorator and some annotations. You can also create a custom component by creating a container and wrapping it. Or you can create a custom component by extending existing classes. So let's look at these. When you create a custom component, it gets plugged into your TFX pipeline exactly like a standard component or any other component. For a Python function-based component, we just add the component decorator at the top, and then in the arguments to the function, we add some annotations to define the arguments to our component. For container-based components, we're just going to wrap it using the container component create container component call. And we want to make sure we specify where to get the image for that container. And we have some artifacts that we're going to pass it. We also have a command that will run when we start up our container. And to extend an existing component by extending the classes, usually we're just going to be writing a custom executor for that. So we're going to subclass the custom executor or the current executor and extend it. TFX is, in addition to being an open source platform, is also available in cloud AI pipelines. At a very high level, this is what the architecture looks like. We're running TensorFlow inside TFX, which in turn is running on top of Kubeflow pipelines, another open source framework. And for cloud AI pipelines, that's running on the Google Kubernetes engine, or GKE, and leveraging the various Google Cloud managed services. So at a little deeper level, this is what it looks like. Again, we have a TFX pipeline. It's running on the KFP SDK using GKE for its Kubernetes deployment. And it also includes Jupyter Lab instance running in a VM. So you can use that to do development and to monitor your pipeline and so forth. At the end of the day, you have the same pipeline that you would have in any other environment. So it could be this one, or it could be one that uses your custom components. And that's TFX. You have standard components, and you can create your own custom components, and you have flexible orchestration and metadata. Here's our webpage. If you haven't taken a look at it, I encourage you to do. And here's some resources to get you started.